Recording has started.
Sona, please.
A very good evening and a warm welcome to everyone present here. Today, we all have gathered here to witness our 12th lecture from the Centenary Lecture series. Today's lecture would be delivered by our beloved alumni, Dr. Arun Kanti Banerjee sir, on the topic of an overview of the theory and application to dynamic of elastic multibody spacecraft, rockets, and underwater vehicles. Today, as our session chair, we have with us Professor Arun Kanti, Professor, Department of Information and Technology, IIEST Shibpur, and our former dean in International Relations and Alumni Affairs. I would request sir to take over the session now. Over to you, sir.
A very good evening to all of you, and good morning perhaps to Dr. Banerjee, Urunda. I welcome you on behalf of IIST Shibpur, formerly BE College Shibpur, to this occasion of 12th Centenary Lecture, which will be given by Dr. Arun Kanti Banerjee. The topic of the lecture is an overview of the theory and applications to the dynamics of elastic multibody spacecraft, rockets, and underwater vehicles. I will give you a brief idea about the speaker. Actually, as a Dean International Relations and Alumni Affairs, I had several interactions with Dr. Banerjee. He has a great feeling for the institute. Dr. Arun Banerjee obtained his BE Mechanical Engineering degree from BE College in 1962 and completed a PhD in Mechanical Engineering from IIT Kharagpur in 1969 and a PhD in Engineering Mechanics from the University of Florida in 1972. He was a lecturer at IIT Kharagpur from 1964 to 1969. He worked as an aerospace engineer at Northrop Corp 1972 to 1976, Martin Marietta 1976 to 1980, and contributions to flexible multibody dynamics. He was invited to be the keynote speaker in an European Space Agency conference in 1992. He has taught 3-week courses at ISRO, IIT Delhi, IIT Guwahati, and at the Beijing Institute of Technology. He had presented papers in numerous conferences in the USA, at Venice and Tokyo, and the international congresses in theoretical and applied mechanics held at Warsaw in 2004 and Adelaide in 2008. He is the author of the book Flexible Multibody Dynamics, published by Wiley in 2016. Dr. Banerjee actually expressed his desire to come to the institute and visit us and deliver a lecture series. However, due to the onset of COVID, that did not materialize. So on this occasion, we'll be very grateful to listen to Dr. Arun Kanti Banerjee. Over to you, sir.
Ask for permission to share content.
I need the permission to need your permission to share the entire screen.
Dr. Das, can you please check? You are a co-host, so I think you should have permission.
Can you see it now?
Not yet. Did you share the screen, entire screen?
Yes, yeah.
Yeah, it's coming.
Yeah, it's coming.
Okay, now you can go forward with this.
Yeah.
Okay. Before beginning, I want to thank Professor Indranam Biswas and Professor Sudhir Ghosh and Professor Bidyut Pal, who never complained about receiving all my slides. I think I gave him 111 sets of slides. And of course, I thank my friend, Professor Amitav Ghosh, he's a distinguished classmate of mine. And I'm really happy to be included as one of the speakers in this Centennial Celebration. And I want to send my admiration and my affection to the young undergraduates and graduate students of the Mechanical Engineering Department at my old college, the present generation. And Professor Arun Ghosh forgot to tell you that I am also an extinguished professor of mechanics. So let me begin. You see the title of my talk. The title of my talk is Dynamics of Elastic Multibody Spacecraft, Rockets, and Underwater Vehicles. So what you see in the slide is first of all, I'm giving some examples of multibody systems. The first example is that of a human being, an astronaut. Actually, the human body is a multibody system connected at hinges. We can turn our head, we can nod, and we can curl up our upper arm, which is connected to the shoulder by a ball and socket joint, and our lower arm is connected at the elbow by a revolute joint, and the hip is connected by a ball and socket joint, and the knees are connected by a revolute joint. So examples of multibody systems are like this. They are a system of rigid or flexible bodies connected one to another by means of some rotational joints. The next slide that you see to the right of the astronaut's picture is that of a helicopter with 4 blades for the main helicopter and a side sort of fan that is required for maintenance of stability. You see, what this helicopter is carrying is a load by means of 2 tethers, 2 nets. This helicopter is actually used to transport things or goods from Antarctica to Argentina. These are real things used to carry stuff from Antarctica to Argentina. On the lower left corner, I have a picture of the Galileo spacecraft, which was sent to study the moons of Jupiter. And on the right lower corner, you see a picture of a spacecraft on which actually I am working. I work half time still because I found retirement very boring. So there's a company very close by, 12 minutes walk from my home. So this system has got 7 reflectors attached to a bus. They call the carrier a bus because it carries goods. So this main spacecraft, there are 3 views shown there. The thing has 6 reflectors, as I said, 2 solar panels, and the bus carries a tank full for thrusting, and the reflectors are connected to the main bus by some small joints, not really small, but articulated joints. So the next one I show, the main work of a dynamicist is that of formulating equations of motion of complex spacecraft. And the reason for that, before they are actually sent out, one has to know how it will behave. To do that, one has to simulate the system, motion of the system, and that means writing some differential equations, the solutions of which will. I mentioned here several methods that can be used to derive these equations of motion. First, I call the momentum principles. All it does is writes the time derivatives of the linear momentum is equal to the force, and time derivative of the angular momentum about the system mass center is whatever the torque is applied to the system. So this tracking the mass center of the motion is important. This is not necessary otherwise, because of the fact we have to take the moments about the system mass center. In D'Alembert's principle, it is the same as momentum principle, except that, as D'Alembert said, that the force minus the mass times acceleration is a zero set, and similarly torque minus the inertia torque is also 0. So these zero-sum vectors, because they are actually 0, actual active force and inertia force. So you can take the moment of 0 about any point. That's the importance. You don't have to take moment about the mass center. So tracking of the system mass center is not needed. And system mass center can be like this. Suppose you imagine the letter C, and suppose the letter C is made up of 3 or 4 bodies. The system mass center will be somewhere in the air between the 4 bodies, because you have formed a C. The system mass center may not be about the any material point in the system. However, the 4 bodies, when they line up to form a line, the mass center is on the 4-body system. So mass center moves. So and that you have to track that in the momentum principle. In the D'Alembert's principle, you do not have to. Then the third method that I wanted to mention is Hamilton's principle, or Hamilton's equations, in which one forms a Hamiltonian function that requires inverting an n by n matrix to get the q dots, or the time rate of change of the generalized coordinates. Now, the example that I showed you that I'm working on, this with 6 reflectors and 2 solar panels, that has got 37 degrees of freedom. So remember, you have to invert this 37 by 37 matrix algebraically. That's a huge task. It will take pages and pages and pages. So this is practically useless. Lagrange's method is the most popular method used in many places. And but if you take up a complex problem, as I'll show you soon, the labor involved is horrendous, you know, and the equations that are also have to stretched out over many pages. And Boltzmann-Hamel equation are a special version of Lagrange's equation, where instead of using generalized coordinates, one uses quasi-coordinates. The meaning of quasi-coordinates is the integral of these quasi-coordinates is not a generalized coordinate. So it's a combination of a linear combination of the time derivatives of the generalized coordinates is called a quasi-coordinate. But this method is the most complex. If you see the steps involved, what is involved to do that. So this is computationally very expensive. And the sixth method is due to Gibbs. Some people call it Gibbs Appel equation. And here one has to form a Gibbs function. It is a function of the square of the acceleration. Now imagine you have a multi-body system and you have to compute the acceleration at one point in one body. It will have terms from the previous bodies also. So it will be a huge expression, and Gibbs says, well, first form the square, and then it's a function of the square of the acceleration, and then he will differentiate it with respect to the quasi-coordinates of Boltzmann-Hamel. So all these first six methods were used in the 19th century. Only new method to come out in the 20th century is due to Thomas Kane, who used to teach at Stanford. He developed a method in 1965, and the method was published in a quarterly journal of applied mathematics. And that is what I use in most of my work. And also that is used in most industrial codes in the USA. Okay, the next slide, I go through some. Now, please tell me when I have to finish. So according to that, I will speed up or go at a pace that is suitable to you. Okay.
Please proceed at your own pace. Please proceed at your own pace.
All right.
Yeah.
Okay, thank you. Most important theorem in kinematics is differentiation of vectors. Suppose you do the differentiation of vectors by itself does not make sense. You have to tell with respect to which frame you are differentiating. For example, imagine a wooden block, a cubical block, and suppose you paint an arrow there. So on one face you have painted an arrow which represents a vector which has a magnitude and a direction. Now if you sit on that cube, then if I ask you what is the rate of change of that vector in the frame on which I am sitting, which is the cube, you will see the vector is not changing because it is painted or fixed on the cube. However, if there is an inertial observer who is seeing this cube flung out, rotating and translating, then he will see a change in the rate of change in the vector. So there is a difference between what frame you differentiate in. Now suppose the vector is expressed in a frame, a B frame, a B for a body, like this. Z1, a function of t times B1, etc. Z2, B2. So in other words, the vector Z is expressed in terms of components of the vector in the vector basis fixed in the B frame. Now you can differentiate Z with respect to time. It will be simply Z1 dot B1 plus Z2 dot B2 plus Z3 dot B3. So differentiation, because it is based on the B basis and I'm differentiating in that basis itself, the first term is easy. But that's not what I want. I want to know how the vector Z changes with respect to the Newtonian frame, N. And I put a superscript to remind people what frame I am differentiating the vector in. So if I differentiate the vector in N, this is the theorem. This is the most important theorem, I think, in kinematics. And it says, if you want to know the derivative with respect to the frame n, and you happen to know the derivative with respect to the frame b, then what you have to do, you have to add an extra term, that is the angular velocity of the frame b in which the vector resides, cross it with the vector itself. So that is the most important theorem in kinematics. Differentiation of vectors in the Newtonian frame is equal to differentiation of a vector in a frame B plus angular velocity of a vector crossed with the vector B. So then there are four basic theorems on velocity and acceleration. Suppose 2 points are fixed on a rigid body B, and you know the velocity of the point Q, and you want to find what is the velocity of the point P. And the point, because they are fixed on a rigid body, that means the distance between P and Q is fixed. It's a vector, the position vector, but its magnitude is fixed because I know point P, I know point Q, both of which are fixed. In such a case, the velocity and acceleration of P is related to the velocity of Q in the following manner. Velocity of P in n, then n being Newtonian frame, is equal to velocity of the point Q, which is 1 point fixed in the body B, plus omega of B in n crossed with the position vector going from Q to P. Okay. Now we have the velocity expression. Now, if I want to find acceleration expression, acceleration is, is just a derivative of the velocity expression in the Newtonian frame. And if you use the fundamental theorem of differentiation of vectors that I put on the top, you will get the line for the acceleration. I'm not going into it. If you do it on pencil and paper, you will see the truth of this. And velocity in n of 1 point p moving on a moving rigid body. This is an interesting case. Suppose an ant is crawling on that rectangular block. So the ant is a point B, which is moving on a moving rigid body. The rigid body translates and rotates. The theorem says that if under such a condition of one particle moving over a body which itself is translating, rotating, the velocity of that point, actual point, is gotten by velocity of that point in the moving frame B, so which I have indicated as V of P with respect to the frame B, and then this rather strange thing, velocity of B bar in n. What is B bar? B bar is actually a point of B which happens to be the image of P at any given instant. The ant is moving, so it casts a shadow on the body B from time to time to time. Those shadow points are actually bodies of B. That's why I put a bar to say it's velocity of the image point with respect to the Newtonian frame. And again, if you want to know the acceleration, you differentiate that with respect to the fundamental theorem on differentiation of vectors. You will get the last line, where the third term, the last line, is you can recognize the Coriolis force acceleration. Then in the next slide, I show, by the way, before I move on, I should say that kinematics is the most difficult part in dynamics. There are a lot of kinematics that I didn't go over, but like how the angular velocity is expressed, I did not go over these things. So suppose you take up this example. One rigid spacecraft G, which has 3 reaction wheels, one W1, W2, W3, and it has got a nozzle for a thruster. The FTA is the thrust force that the spacecraft needs to move on. And then there is a mass spring dashpot system, which is actually, you can think of a particle moving over this moving body. As the mass spring dashpot causes the particle to move, that would provide a case for a point moving over the moving body G. And then this slosh, fuel slosh, you see is shown as a pendulum attached to the axis of the spacecraft. Fuel slosh has been studied extensively by a company in San Antonio, Texas. They did lots of experiments, and they showed that you can approximate the behavior of fuel slosh by the motion of a pendulum. They verified with tests. So that tells, and depending on the amount of fuel, what happens is the attachment point of the pendulum moves on the axis of the spacecraft. So this is just an entirely fictitious representation, but tests have shown that this is a good enough representation of fuel slosh. Okay, and before I change the slides, I should tell you that these reaction wheels, W1, W2, W3, are used to control the attitude of the spacecraft. The spacecraft drives the wheel, and in return, by a torque, and in return, the wheel provides the reaction torque in the opposite direction. That's why it's called a reaction wheel. Spacecraft drives the wheel by a motor, and the motor frame gets a reaction torque, and the frame being the spacecraft. So if you have three wheels, you have three axis torque on the body, which is sufficient to change the orientation of the body. Now, I don't know whether you see it. This slide got mangled. I don't know at what stage, but I'm describing Lagrange's method. Lagrange's method requires that first you form the kinetic energy function, and then Lagrange says, Lagrange's equations the equation that you see at the top is only a recipe. It's not the equation of motion. The recipe is this, that form the kinetic energy function, which will be a function of the generalized coordinates and their rates. If there are n number of generalized coordinates, this is what you have to do. Take the derivative of the kinetic energy with respect to the ith generalized coordinate. I can go from 1 to 9. For example, for the problem I am doing for this company locally, n is equal to 37. There are 37 degrees of freedom. So there are 37 QIs. So differentiate the kinetic energy with respect to QI. Then you do perform two more differentiations. Differentiate the kinetic energy with respect to Q dot. You don't see the dot because of the blurring, that my computer or whatever I did produced. So here, what you are doing is, we are taking the derivative of the kinetic energy function with respect to Q dot, and that result I am differentiating with respect to time. So note that there are three differential equations per generalized coordinate. I differentiate the kinetic energy with respect to the coordinate itself, differentiate the kinetic energy with the derivative of the coordinate. That result I differentiate with the time. So three differentiations per generalized coordinate. So if there are 37 generalized coordinates, you can see for this complex example of the spacecraft with the nutation damper and three wheels, you see even for that system, which is n equal to 12, not 37, this is a formidable amount, long expression. I showed it for the fun, like a person getting a pleasure out of the misery of something else. So that's how I showed. This is the misery that you have to go along with. Impossible to form Lagrange's equation for the problem that I showed you. Okay? So that is why Lagrange's equations cannot be used for complex problems that spacecraft industry uses. It's very easy to show it in textbooks, because usually textbook authors show with simple examples, double pendulum, etc. It makes sense because it shows the essence of how to proceed. But now if your salary depends on whether you can write the equations of motion, for these generalized coordinates, for this example that I showed before, you cannot do it because kinetic energy is equal to such a long expressions and you differentiate 3 are generalized coordinates. So Lagrange's equation is a bad way to go for a large problem. And now in contrast, so in other words, you cannot solve the problem. In contrast to that, if you use Keynes' method, you will get the result. And I've given some 2 nice examples. Suppose you have a pencil which is spinning about the axis of the pencil, and it is spinning. In the example problem that I have, we wrote a paper on this. The minimum axis of inertia is B2, the second axis of the body. Now, if you spin it about minimum axis of inertia, which is the length of the spin, along the length of the pencil, then what will happen due to dissipation, which is provided by the nutation damper, the pencil will, the spinning pencil will start to slant, form a cone. The cone will increase, just like a symmetric top, and finally the the pencil will fall down onto the ground and start rotating on the horizontal surface. So minimum axis inertia, you start the spin, but the object is unstable and goes from spinning about the minimum axis to the maximum axis, which is the transverse axis of the pencil. So it will start rotating on the flat plane, turning about a maximum axis. And I show here how the angular velocity. Remember, the axis 2 is the minimum axis of inertia. The axis 2 inertia goes to 0. That is when it has fallen down on the ground. And this is what happens for a minimum axis case. With a nutation damper, the falling down takes a long time, 10,000 seconds or so. For that example problem, we are still considering that body with sloshing pendulum, 3 reactions wheels, and a nutation damper. We are still working on that problem. Now, if there's a nutation damper present, by the way, the word nutation means nodding. Like if you are greeting somebody and you nod your head, that's what nutation means. So or another way is to say wobbling. So the pencil rotating about the minimum axis of inertia will wobble or nod until it falls flat. So with nutation damper, the falling flat time is about 2000 seconds or so. Now, I show what happens to the maximum axis of inertia when it is rotating. This result shows how the maximum axis rotation, when the pencil was rotating about the minimum axis, it was 0, and gradually it goes up. And if there is no nutation damper, it takes a long time to reach its final spin angle, spin rate. If there is a nutation damper, the final spin rate is reached sooner, and energy dissipation causes the spacecraft to go to flat spin about the maximum axis. This is a very interesting result in spacecraft dynamics. And sometimes, when you carry a fuel, the fuel invariably has a viscosity, so there is damping inherent in it. So you do not specially need a nutation damper that will give you this kind of a behavior. This was predicted in 1965, and it indeed happened. Now, suppose you want to reorient a spacecraft from one direction to another. What does it happen? to do that, you have to write these equations of motion for the system and solve it, and then it will teach you, yes, this is what you will behave. So suppose you want to maneuver the system from when it is rotating about a maximum axis, which is in this case axis 1, and axis 2 was the minimum axis of inertia. And suppose you want to turn the spacecraft from rotating about maximum axis 1 to maximum to rotation about maximum axis 3. So basically, you are requiring a 90-degree turnover. And the solution of the differential equations that describe the equation of motion for this thing produces these three curves: how the maximum axis inertia behaves, how the medium axis inertia behaves, and how the two, remember, 2 is the minimum axis. The 2 behaves like, because it falls into flat spin, is magnitude is 0. And the 90-degree rotation is shown here. Spacecraft first starts spins about axis 1 with axis 1 up, then a torque is applied by the wheel, and so all this thing is done by turning a wheel on. If you turn the wheel on in a certain direction, then the wheel will impart a negative torque onto the on the spacecraft. So you actually, with the turning on of the wheel about axis 3, the spacecraft torque will be applied in a minus axis 3 direction, and then spacecraft pitches over by 90-degree and reaches the axis 2, which will eventually make it fall down. All these things were predicted by the simulation. Okay. Next, I wanted to show that Lagrange didn't get the solution and Keynes' method did give the solutions. I want to tell you what is Keynes' method. The method like this. Keynes' method starts with defining a quantity which he calls generalized speed. Lagrange uses generalized coordinate. What Keynes uses is a speed type quantity, and he uses the symbol U. And sub I means how many degrees of freedom are there in the system. So for this spacecraft with nutrition damper and 3 reaction wheels, we had, and a sloshing pendulum, we had 12 degrees of freedom. So you have to introduce 12 generalized speeds, UI, U1, U2 through U12. Now, having introduced this generalized, so this is the relationship. The UI, the generalized speed, is a linear combination of the Q dot. Unfortunately, this rectangle is it messes up things, so you don't see that there is a dot over there, QJ dot. So AIJ QJ dot plus some other terms. B does not contains QJ dot. Whatever contains QJ dot is AIJ QJ dot plus this is equal to the ith generalized speed. Then Keynes says, okay, form the velocity of the particle using those generalized speeds, and it will be seen that if you express the velocity of a point P, it will be the coefficient, the generalized speed times by a certain quantity, which I have written down as VPI with respect to n. So it's this quantity VPI is called the ith partial velocity of P in n. So this is a strange creature. It is the coefficient of the ith generalized speed in the velocity expression that goes with, so if you write the velocity expression involving these generalized speeds, you will get terms which are U1 through U12, etc. The coefficients of the U1, U2, U3, Keynes calls the ith partial velocity if you collect the terms in the velocity expression having to do with UI. So for example, if for a 12-degree freedom system, there will be VP1 U1 plus VP2 U2. So VP1, VP2 are just the coefficients of the U's. U that you use, U1, U2, U3 that you use in writing the velocity expression. So coefficients of that generalized speeds is called the partial velocity for that generalized speed. Similarly, you can do, and you have to do, sum it up over all the degrees of freedom, in this case 12. So angular velocity is similarly expressible at some linear combination of the generalized speeds. Remember, UI, I'm calling them as generalized speeds. And the angular velocity one can write as linear combination of that generalized speed times quantities that I'm calling omega bi in the n frame. So this is the this quantity omega bn sub I is another strange creature in Keynes method. This is called the ith partial angular velocity. Why do I call it ith? Because it goes with ui. These two things, the partial velocities and partial angular velocities, are central items in Keynes method. Now, then what we move on to is form what Keynes calls generalized inertia force. So if a system has got np number of particles and nb number of bodies, this is Keynes' recipe for forming the generalized inertia force. F star I will go from 1 to number of degrees of freedom. So this is what inside a square bracket. You form the inertia force, mass times acceleration, dot it with the ith partial velocity. And then in the curly brackets, this quantity I dot alpha plus omega cross I omega is the inertia torque, you know. So I alpha is a vector because I is not a vector. I is called dyadic. Have you heard of dyadics? Dyadics is a mathematical operator dotted with a vector. It produces a vector. So this term is a vector. This is again what we do is do omega cross. This is just using the first theorem of kinematics that I mentioned. So I differentiate it in the B frame first, and then omega B crossed with the vector. The vector being inertia dyadic cross dotted with angular acceleration of the body. So the term within the curly bracket is multiplied by the partial angular velocity of the body itself, of the jth body. And now J goes from 1 to the number of bodies. So sounds complicated, but it's very systematic. First form generalized speeds, then write the velocity, expose the coefficients of the generalized speeds. In velocity, they are called a partial velocity. Expose the coefficients of the generalized speed in the angular velocity expression, that is called the ith partial angular velocity. Those are used in forming the generalized inertia force. So minus ma is the inertia force, dot multiply that with the ith partial velocity of the particle, and that I goes with the number of degrees of freedom. And then here inertia torque is multiplied by the ith partial angular velocity. Again, what is partial angular velocity? It is the coefficient in the angular velocity expression of the ith generalized speed. And there are remainder terms that we don't have to worry about. So this is how the generalized inertia is formed, by dot multiplication of the inertia force with the partial velocity and the inertia torque with the partial angular velocity. You do it as many degrees of freedom as there are. So form, for this problem, 12 generalized inertia forces. Generalized active force, a name given by Keynes, is obtained like this. If on the particle Pj, jth particle, there is a force Pj, dot multiply that force with the ith partial velocity and sum that quantity for all the bodies, np number of bodies. And then on the rigid bodies, if there are nb number of rigid bodies, form this sum, following sum. Place the the force on the jth body at the mass center, and take the dot product of that partial of the ith partial velocity mass center. the mass center that I called a BJ, I call it BJ star. You know, BJ star is actually the mass center of BJ. You know? And then I take a dot product of the torque on BJ by the ith partial angular velocity on BJ. These two terms arise from the fact that if the force is acting at a point different from the mass center, you can always replace that force by showing an equal and opposite force at the mass center. So when you have a equal and opposite force at the mass center, you have added nothing extra. However, you have done something very clever. You have formed a couple between the positive and the negative vectors. You formed a couple. That couple has a torque at TBJ, and you have brought over the force acting point different from the mass center onto the mass center instead. This is an idea of replacement of a force by a force and a couple. So T is the torque and F is the force. So after you have formed Fi star and Fi, you just add up and set it equal to 0. That is Keynes' equation. And these equations are formed for each generalized speeds I goes from the from 1 to number of degrees freedom for the spacecraft with 3 wheels and sloshing pendulum, and the body itself can rotate and translate, and 3 wheels. You have to form 12 equations. But note the reduced flavor in Keynes' method. All you do is just take dot products rather than take 3 differentiations required in the left-hand side of Lagrange's equation. That is where the saving in labor comes. You just take dot products to form the generalized inertial force, generalized active force, and you have to remember how you form the partial velocity. These are the coefficients of the generalized speeds in the velocity expression. Partial angular velocity is the coefficient of the generalized speeds in the angular velocity expression, and the generalized speeds themselves are formed in a linear combination of the q dots. So this is all about Keynes' method. I'll show you now. Again, this time I take up the role of a teacher who wants to the students to know the idea behind the methods. So here again the thing was all messed up. Q1 is equal to, I take, here is this angle Q1 and there is the angle Q2. So I say, well, I'll take the first generalized speed as Q1 dot, this Q1 dot. The second generalized speed, so you can say, well, I had initially told you that integral of the generalized speed is not the generalized coordinate. I have violated that rule here, but wait and see. Now I define the second generalized speed as Q1 dot plus Q2 dot. If you see that if I integrate U2 and if I integrate the right hand side, it will not be Q2 dot, but it will also have an Q1 dot. That is why this is called a non-integrable quantity generalized speed. So from these two equations, you can get that time rate of change of the generalized speeds Q1 dot, Q2 dot. And one rule for experienced dynamicists is that make the generalized speed expression as complicated as you can. It will pay off later. You'll get very simple equations. I won't go into that now. So in terms of the generalized speeds for this double pendulum, first you find the velocity of this pendulum. This is omega is Q1 dot. Q1 dot is U1. So U1 times the length of this thing I have written up in the N1, N2 basis. And this is the result. This cross this gives this. The velocity of Q is from the theorem in kinematics. Here's a rigid body. 2 points involved, 2 points are fixed on the rigid body. If I know the velocity of this point P and want to know what the velocity of the point Q, that theorem said what you got to do. So velocity of P plus omega cross that position vector. So in this process, I found both the velocity of P and the velocity of the point Q. And now I'm going to construct the partial velocity table. I say I is the index for the degree of freedom. when I is equal to 1, and this is the ith partial velocity of P, this is the ith partial velocity of Q. So look at the expression to find for I equal to 1, in the velocity expression for P, look at the expression for U1. This is the velocity expression. The coefficient of U1 is L times this. That's what I've shown here. L times this is the first partial velocity. Now, second partial velocity should be the coefficient of U2 in the velocity expression P. Velocity expression P does not contain a U2. So the coefficient should be 0, and it is shown 0 here. Now take up the point Q. The first partial velocity of this should be the expression containing U1. And U1, I said that it is equal to Vp plus something. Vp was this. There is indeed a coefficient of U1. That is L times the thing within the parenthesis. That is what I have shown. And that thing being the same as Vp1, for the sake of brevity, I wrote it Vp1 itself. So Vp2, if I want to compute Vp1, for this example, it is Vp1. I want to know the first partial velocity of Q. So it says find a first partial velocity of P. First partial velocity I have found already. So it is that then. Now, if I want to know what is the second partial velocity of Q, in this expression for Q, which contains this plus the big one, the first term from velocity of P does not contain a U2. However, U2 is present in the expression for Q, and the coefficient is U2 crossed with this quantity. That is what I've written as the second partial velocity of the point Q. So Q has a first partial velocity and a second partial velocity, because there are 2 degrees of freedom. I is the degree of freedom. P has only a first partial velocity, no second partial velocity. Now, to proceed with Keynes' method for this 2 degree freedom double pendulum problem, first Keynes says find the accelerations. So I just differentiate the velocity and of P and velocity of Q, remembering the theorem that I said is the most important theorem of vector differentiation. This, and then the generalized inertia force. The first generalized inertia force is the inertia force on P dotted with the first partial velocity of P plus inertia force of Q, because remember there was a summation in the definition. So inertia force on Q dotted with the first partial velocity of Q. These quantities that I formed in the table, the partial velocities. Similarly, for the generalized inertia force corresponding to the second generalized speed is inertia force times the second partial velocity of P, then again inertia force on Q times the second partial velocity of Q. So the step 2 forms the generalized inertia force. Step 3, first you have to know the forces. The forces are due to gravity on particle P and particle Q. Now, generalized active force is called the force on P multiplied by the first partial velocity. If you want to form the first generalized active force, then multiply this system with the first partial velocity. Force on P times the first partial velocity on P, force on Q times the first partial velocity of Q. And if you want to form the second partial generalized active force, it is the force on P dotted with the second partial. If I want to find the second partial generalized active force, then I multiply by the second partial velocity for both P and Q. And notice that the generalized active force is not a vector. This is a scalar actually. And same thing is with a generalized inertia force. This is not a vector because there's a dot product going on. So Keynes' equation is the sum of the generalized active force and the generalized inertia force equal to 0 for generalized speed number 1, generalized speed number 2. This is it. Now, I apply that to a more complex problem, the shuttle-borne tethered satellite problem. I worked on this at Northrop. I wrote the equations for it and coded them also. The space shuttle is going at an orbit of 220 kilometers. NASA had the idea that can we lower a satellite by means of a cable, such that a 100-kilometer cable, such that the lower satellite is going only at 120 kilometers. That way, the lower satellite will be able to see with a keener sight because it is a shorter distance from the Earth. So that was the motivation. So shuttle goes at 220. The satellite, the nth, I represented, by the way, this tether by means of some lumped particles connected by springs, because the tether can stretch, So tether is modeled as a set of lumped mass springs connected by one-way springs. In other words, the springs cannot go slack because the tether is not allowed to go slack. That will not be physical modeling, physically realistic. So I show the tether, by the way, is wound up on a winch on the shuttle bay and is reeled out by a motor. So lower curve shows how the length of the tether changes. So in 25,000 seconds, it goes from 0 to 100 kilometers. And the in-plane angle of the tether is swinging like a pendulum. So the in-plane angle goes from 0 to this and finally oscillates at this. And the tension you see goes to then later there's a shady kind of band. Why? Because as you are bringing it closer, Earth's gravity wants to pull the satellite down. So you have to, pull back, as though you don't want to let it go and get gravity grab it. So you are applying a brake as though. So that you are hauling it, you are putting tension onto it to bring it back. That's why there is a hash mark there. So this is the snatch load. You're bringing it in as though you are breaking it. You don't want to let it go away due to pull of gravity. You want to bring it in, So in the beginning, there is not much. The gravity is not strong, but towards the end, as you come closer, and in the previous version I showed, I have modeled it with many particles. As one particle changes from 5 particles to 4 particles to 3 particles, there is a snatch. I'm changing 5 to 4, 4 to 3, etc. So the tether tension behaves like this. Physically, you can think of it as pulling on so that it does not escape. Now, here I show the tether satellite retrieval. Now, if you have played with a yo-yo, you will see that if that yo-yo, little ball at the end of the string, if it swings, then when you try to bring it in, the ball at the end of the string will try to wrap up on the wheel of the yo-yo. Now, in this case, the subsatellite connected by a tether would want to wrap up around the tiles of the space shuttle. NASA would never allow that. The satellite comes and bangs the tiles. NASA would never allow that. So the idea was, and I think Professor Keynes, who was a consultant to NASA, he came up with this idea that why not put a thruster so that when it is coming very close, the tether will pull back away from the shuttle, And also, tether tension at that time is very low because, the end of the tether, like let us say the tension is, you have the only 10 meters of cable remains. So the gravity at the 10-meter point and the orbit point is practically the same. That's why the tether can go slack, because the tension in the small segment of tether is not much. because the end of the tethers, the gravity at those 2 points is essentially the same. So the tether tension between those 2 points, the 10 meter long end and the shuttle exit point, is very small because the gravity at the, so that's why it goes slack. And if you fire a thruster, the slackness will be prevented. So one curve showed the tether tension, and another curve shows the in-plane angle, and this is the outer plane angle. In one case, the tether length was 150, and in another case, starts with 100. Okay, so this is about tethers. Then another thing that I did was, again, based on reading Keynes' book. I read Keynes' book when I was at Florida. My teacher was a former student of Keynes who was not a good teacher. He was just essentially copying Keynes' class notes. So the good thing that he did was he prescribed Keynes' book. And we had a small room. I had a small table with a table lamp. I can tell you, I did all the problems in Keynes' book. And that's how I learned. So anyway, here's the problem. The solid rocket booster was used in those days to push up a satellite. And on the top of the solid rocket booster, these satellites used to go previously, and after launching the satellite, the booster would fall into the ocean and would be smashed into pieces because the water behaved like a solid stone when the rocket falls from 60,000 feet or so. So the idea was, is there a way to attach a parachute to the booster so that after it has thrown off the satellite that it was trying to boost, the parachute would inflate, and then it will slow the descent of the rocket gently on the ocean surface, and then a ship can go to pick up the booster. So that was the big idea. Now, how the parachute was involved in this case? They placed the parachute on the conical top of the rocket. So there are layers of parachute packing there, and this parachute pack was encapsulated by this cap. And then there were 4 bolts, that connected the body of the rocket to the flanges of the cap. Now these 4 bolts were blasted off, but no blasting would produce exactly at the same instant. So there will be some sort of a kink. The one bolt has opened up some microseconds before other. So it will start with a little bit of a tilt, and then it goes out on the parachute in a ding dong manner. It's a rattling manner, and when it rattles, it hits the parachute package, and it may dent it, so produce a hole. And a parachute with holes is no parachute, So the idea was that to have a cable at the inside of the nose cap, and let the cable be attached to the parachute package, and as air gushes in to separate the cap away, the parachute will turn this way and that, and it may slide backward, slide forward, and then it may have a normal impact. So one of my colleagues did the simulation. I wrote the equations, and he knew how to plot successive configurations. He plotted these things for me. You see, it shows the parachute in one instant was like this, and the final instance was like this. So these are some successive time plots of the orientation of the nose cap. And this the lower figure shows that what was happening. There is a slip forward, at that instant, then slip backward here, and then no slip. So no slip means normal bounce back, and slip forward means it's a sliding impact in the forward direction. A slip backward means it's a sliding impact where the nose cone goes backward towards the booster, staying on the parachute surface. After I did this thing, the chief dynamicist at Marshall Space Flight Center was so impressed that he asked the general manager at Northrop to get this guy US immigration. And when a powerful company like Northrop does that, well, you are going to get it. That's how I became an immigrant. Okay. Now, I'm going to flexible bodies. Now, the velocity, now here, I'm going to find the velocity, the generalized inertia force, and another quantity called modal integrals for an arbitrary flexible body. So, and I assign a vector triad B1, B2, B3 to a frame with respect to which the body is supposed to be deforming. So this body is rotating and translating with respect to a Newtonian frame, and frame for the flexible body. By the way, the word frame and rigid body mean the same thing. So there is a reference frame with respect to which the actually elastic body deforms. The deformation I have shown here as vector delta. So how many, for a flexible body, how many degrees of freedom you need? First, you need, for example, if you resolve the velocity of the point O in the Newtonian frame along the body axis B1, B2, B3, you will get 3 generalized speeds, because you're taking a dot product of the velocity with respect to a vector. So it's a constant. Generalized speed it's not a constant, it's a variable, but it's a scalar rather. So then you add 3 more generalized speeds by taking a dot product of the angular velocity with the ith basis vector. So you have U4, U5, U6. Then you represent the elastic deformation as a vector. It has a deformation also has an XYZ component. So this is a Rayleigh's superposition principle. You multiply the first mode times the generalized coordinate, second mode with another generalized coordinate. You keep, let us say, new number of modes. So it will be total number of generalized speeds. We had 6 there, then add new number of modes, 6 plus new. So this arbitrary flexible has got 6 plus new number of modes, generalized speeds, where new is the number of vibration modes that you are keeping. Now, velocity of this point can be written by the following process. Remember, I told you how to find the velocity of a generic particle moving on a moving frame. You can think of this generic particle G, and as it vibrates, that particle actually moves on this frame, is it not? It's a particle that is moving with respect to this frame. So here you need to have the image point that I spoke of in one of the theorems of velocity. And so this will involve generic particle moving on a moving frame. So that's how it comes about. Basically, the material point moves over the frame itself, And then generally the inertia force I do using Keynes formulation. This is mass times acceleration. dm times this is the inertia force with a minus sign. And I dot multiply by the ith partial velocity of that point. Ui is the ith generalized speed. If I do the dot multiplication of the inertia force with the ith partial velocity, I'll get the ith generalized inertia force. Now, in carrying out this integral, it turns out that the expressions are simplified if you can define certain constants. These constants are called modal integrals. These are characteristically appearing entities in a flexible body dynamics math model. These integrals have to be pre-computed using a finite element code, which has at any node, it tells you what is the nodal mass, it tells you what is the XYZ coordinates of that nodal mass, and what is the vibration mode shape at that location. Using these 3 informations, you can define 9 modal integrals. That is there in my book, and of course, I am not going to tell them what they are now. Now, there is a thing called premature linearization and subsequent correction. If large motion equations, by large motion it is translating and vibrating and rotating. If large motion equations are written for flexible bodies, starting with linear velocity or angular velocity, as it happens when using vibration modes. See, vibration modes come out of a eigen, which is based on a linear mass and stiffness matrices. So vibration modes are gotten out of a linear theory. So if you use the linear theory in the velocity expression, then those equations are said to be prematurely linearized, and it will produce an error. So you cannot use vibration modes directly in writing velocity. If you do that, you have prematurely linearized and equations will be wrong. And let me tell you that a large number of courts in USA and internationally had that mistake. They just did not realize it because they did not put a stringent enough test. Jet Propulsion Lab had this error in their codes, And then I'll show you how premature linearization is corrected by after the fact addition of geometric stiffness due to inertia forces. Actually, myself and one of my colleagues who had a PhD from UC Berkeley, working together, discovered this fact that if you have geometric stiffness due to inertia forces, if you can compute, add to the wrong equations, then you will get the correct equation. That was a beautiful thing for which the European Space Agency called me. There are more to go about it. Suppose you have a turntable and of radius r, on which there is a massless rod, at the end of which there is a particle of mass p. Now you can write the velocity of this particle, and in that expression there will be sine q, cos q kind of things. Now if you neglect the signs, not quite neglect, but say sine q is equal to q and cosine q is equal to 1. If you do that in the nonlinear expressions for velocity, you will get this expression that I write here with a tilde. Velocity of p in n with a tilde. That means it is a linearized. My tilde sign means it has been linearized, assuming sine is equal to the angle itself, cosine equal to 1. Now if you use either Keynes method or Lagrange's method, because Lagrange's method can handle these simple problems, you will get an equation like this. What it says is, here you have U1 dot. U1 dot is equal to Q1 double dot. U1 was taken to be Q1 dot. So U1 dot is Q1 double dot. And this term you can recognize something with Q is like a effective stiffness term. Normally with a pendulum you have minus K by ml square. Now here there is a subtraction by minus omega square. Now, which says that with rotation, the stiffness decreases by the square of the rotation speed. Omega is the rotation speed. Now, that is a physically incorrect thing. When you turn a table, the rod would want to stay straight due to centrifugal forces. It will be harder to change the angle, Q1. So this is a wrong equation. The wrongness of the equation will be small if the speed is small. Speed of rotation is small compared to the natural frequency of the system. This is a key item. Sometimes these wrong equations are used and people are happy. Why? Because the speed of rotation is so small compared to the natural frequency that it doesn't matter that much. However, if the rotation rate is large, then it can even have a negative spring, and negative spin means it will just blow up. Instead of a sine cosine solution, it will have a sine hyperbolic, cosine hyperbolic kind of solution. Okay. Now, this wrong equation you can redeem into goodness by adding geometric stiffness due to a load. Geometric stiffness is actually dependent on loads. In this case, I can compute the load in the reference state, which is the axial force is m omega square r plus L. Due to that, the geometric stiffness force is this quantity, what kg is the geometric stiffness term. If you add this geometric stiffness times q to this wrong equation, you will get this equation. U1 dot, or in other words, Q1 double dot equal to this thing. Now you see something is added to the natural frequency. So it is becoming stiffer with speed. And that is what physically happens. Stiffness increases with spin. Now, we tried that process with a cantilever beam attached to a shaft, where the shaft is being spun up, to some steady state. Now, if you do the this system has got some natural stiffness, EI by L kind of thing for a cantilever beam, and then if you compute the geometric stiffness due to the inertia loads, the inertia force is distributed. If you compute that, have them ready, then if you spin it, you will see that the beam wants to stay straight. Inertia, which in another way it is called laziness. The beam is lazy. It doesn't want to go with the route. It is basically lazy, or it is inertia. So when the base moves up, the laziness of the beam or the inertia of the beam causes the thing to stay back, and so the deflection increases. Then the beam rather reluctantly catches up and oscillates like this. So this is the behavior of a correct result of beam spin up that was obtained by adding to the incorrect equations obtained by premature linearization, adding to that geometric stiffness due to the inertial load. And if you don't do add the stiffness, this is what will happen. The deflection will become unbounded. I did the same thing on a plate. I wrote this paper with Professor Keynes. Actually, the beam paper also did with him. So Keynes had called me from Florida, and that's a long story. So here was a plate which was rotating about one edge, and it's a fixed. All these sides are fixed. So the plate has all four edges. Like a cantilever end, and spin up of a edge. The plate can be a gas turbine blade, or sometimes it can be the wind turbine blades also. So they are rotating, and again, if you spin it up about the R2 axis of the plate, then again the laziness or the inertia causes it to lag, causes it to lag the base about which it is fixed. Remember, the plate is rotating about the R2 axis. So when the rotation goes on, initially the middle point shows its laziness. So now at the end, it will, when it is sufficiently gone farther, then the midpoint of the plate rather reluctantly joins with the frame. So you see the tip deflection is like this. And we plotted also what is how the dynamic stiffness, the ratio of dynamic stiffness to natural stiffness varies. So with speed. And this is the curve. It becomes stiffer with spin. Then I did another formulation of for an experiment that NASA and the scientists at NASA wanted to do. The program was called WISP. WISP stands for Waves in Space Plasma. And I don't know what they wanted to do with it, but I know the mechanism what they needed. 250 long beams were attached on the shuttle bay, and the shuttle was asked to yaw. Yawing means perpendicular to the axis of the shuttle, and the shuttle yaw rate was 1 revolution per 1200 seconds. Okay, so it's slow rotation. So now, if the base is slowly rotating and it's a thin tube, 150 miles long, 450 feet or so long, then you can see that it will have large deflections. The base is attached here, the tip at 150 meters or 450 meters away will bend quite a bit. How I modeled it was, here is the shuttle, the square that you see. And then I broke it into rigid segments and connected them with torsional springs. Okay. And I wrote the dynamics of this thing using a procedure that is called order n. It depends, it is called order n because the arithmetic operation count for that formulation it varies with the number of degrees of freedom, or how many cuts you have given to the beam, you know. So, and now typically because the deflection will be large, so this goes beyond linear theory of elasticity, and one has to consider nonlinear theory of elasticity via finite element codes. So one of our guys, two of our guys, had PhDs in civil engineering from Berkeley, and I worked with them on this problem. So I did it using rigid rods connected by springs. They did it using the good nonlinear finite element. I don't know anything about nonlinear finite elements. And we produced our results of our two codes. And you see, it plots the deflection. Deflection reaches about 70 meters, or a little bit more than 70 meters. So 150 meter long beam off the original axis, the tip moves by nearly 75 or so. The interesting thing was the crude model of rigid rods connected by springs and this sophisticated model of nonlinear finite elements, they essentially agreed. But on the side of computation time, my order n formulation was 25 times faster than the finite element model simulation. So it's an algorithm. You know, it's a complicated algorithm that I did not generate. It was generated by one student of Professor Keynes called Dan Rosenthal. I just used his method to this problem. Okay. It's a recursive algorithm, 3-pass recursion. And this is my major work in my life, flexible multibody systems. If you write the equations of motion of a system of bodies containing many flexible bodies connected as hinges, if you write by Keynes' method, you will get. I'm quite vexed by the markings on my slides. So the equation is mass times u dot. Remember, u is generalized speed. So u dot is and generalized speed has the dimension of speed, and u dot will be having the dimension of acceleration. So it's basically mass times acceleration is equal to force, but it's just to give you an idea of the physical entities. It's actually not really mass, physical mass times physical acceleration. So mass times derivative of the generalized speeds is equal to right hand side. If you apply Keynes' method directly, this mass matrix is a dense matrix and it's a time varying. So if you have a 37 degree freedom problem, the operation count will be 37 cube, you know, or if you have a 12 degree freedom problem, it's a 12 cube. So decomposing and back solving will be quite expensive if you go to higher and higher degrees of freedom. I developed an algorithm which I'm not going to talk about because it will be, I cannot convey it in even 3 or 4 hours. Actually, I can, but it is written for specialists. So, this is the paper that I presented at ESA, the European Space Agency. In this formulation, it has a block diagonal. It comes up with the block diagonal mass matrix, and in addition to that, it includes the geometric stiffness phenomenon that I talked about due to 12 inertial loads. That's what my friend from UC Berkeley, he was a civil engineer, he taught me how to compute geometric stiffness due to inertial loads. So I told him these 12 inertia forces arise. Can you tell me how to get this geometric stiffness? He said, well, I'll go to my general model, put in your inertia loads, Inertial loads come from rigid body guys like myself. So we produced a 12 set of geometric stiffnesses in formulating this equation, and there is a special algorithm backward forward this. So for example, for this body, for this 4-body system, you may have a first body 6 by 6, and then you have some rotation angles for the first flexible body. So you see a small submatrix followed by a big matrix is the order, and the lowest submatrix is the 6 by 6 matrix for the bus. And then I also had a constrained block diagonal formulation. This was the theory was tested against a lab experiment. The idea was to see the unfurlment of an antenna. Here is this dish-shaped antenna, which was made out of ribs, which were segmented. Each segment was was made up of several parts. Each part was connected one to another by torsional springs. So these are tapered beams with the tapered beam connected one to divided into many parts, each part connected to its neighbor by torsional springs. And this antenna is and there are cables or something like that moving, so or wire meshes. Initially, it is stored into the spacecraft. So it's like a package wound up around the spacecraft, and then there is a stop that stops the wrapping around of the ribs, and then the stop is released, and that it just opens up like an umbrella opening up, and so as it opens up, there are some torque loads that are applied to the attachment. This was a lab test actually of how it will behave in space or in 1G, So as the antenna, which was initially wrapped up in a package, several layers of wraps, and then some release was put into that wrapped rib process, and then it unwraps, and it becomes like an opening of an umbrella, and with that there's a huge torque load. As this is open, that torque has to be transmitted. So by action and reaction. So here it is transmitted. They had some strain gauges to measure, and they had a cable when they wanted to measure what would happen in 0G. So the weight is balanced by that cable. Now, in one experiment, they measured the shoulder torque in the x direction. Here is the x direction. They measured the shoulder torque as they measured, and what was predicted by my theory, the block diagonal theory. Look at the beautiful match. Considering that we did not exactly know the elasticity coefficients, the mass, and moment of inertia, all these things, won't you call this as a beautiful match? In fact, one of the reviewers of my book said so. Then I also went to study a thing for the Naval Postgraduate School. The idea was there was a ship. The ship would deploy by means of a cable a sonar device that would send out signals to detect if there are mines deployed on the sea bed. If there's a mine and the ship comes over it, it will blow up the ship. So what they did is, to prevent damage, they said, okay, we'll send a sonar device by means of a cable, let it find out where the things are, and if it is damaged, or this inexpensive thing will be damaged. And it has a control system which tells where to go to search for this buried mines. And I worked this with a Vietnamese PhD person from Stanford. By the way, the city I live in is where Stanford University is located. And he plotted successive time plots of the shape of the cable. So it forms a C-type shape, or a J, inverted J-type shape. And the cable deployment length was like that. Okay. Now I show the dynamics of a rocket, including geometric softness in this case. Why do I not speak of geometric stiffness? It's because of this. The engine gives it a thrust to the rocket body, which pushes the rocket forward. And then inertia force due to that push will be in the reverse direction, because force is whichever way it goes, inertia force is, or the laziness magnitudes will go the opposite way. So the force is pushing from the due to the engine, inertia force is going reverse the thrust force. So these are two forces equal and opposite, and they will compress the rocket. If the rocket is small enough, then with these two forces, they can buckle. In fact, that is what happened in many rocket flights. The rocket bursts out at the launching pad due to this stiffness. Because these stiffness are compressive, they actually make the thing softer. That's why I've called it geometric softness rather than geometric stiffness. And geometric stiffness, as I told you, is always associated with a load. So due to this load, then wrote the equations for it, used an order algorithm, and these are the results. It says the horizontal displacement versus time and height versus time shows that the highly flexible rocket, which is shown by the dotted points, and the solid line is rigid model of the rocket, are quite different. It says that if you look at the horizontal curve, horizontal displacement is less with a flexible body model than with a rigid body model. In other words, if you don't have a flexible body model, you would think that you can land at 500, 60,000 feet away. But no, reality is you will land far shorter. It will land, I think I messed up something here. If I have a rigid model, I have this, it will go a shorter. I see. I was measuring in a negative direction. So it will go in negative direction 60,000 feet, and the rigid model will predict. Actually, the elastic model will say it will go even beyond. So actually, I wrote something wrong here. It is a greater distance, and also in the height, the rigid body model, actually different things happening in the two cases. The rigid body model reaches higher. So if you want to kill an enemy plane, which is flying at 90,000 feet or so, you can do that with a rigid body model, which is actually unrealistic. No rocket is a rigid body. Now, if in a real situation, a flexible body situation, the rocket will not be able to reach the plane that you want to smash. So you better have a flexible body model to know if the rocket would hit an enemy plane that is flying at 90,000 feet. No, it does not go that high. On the other hand, the flexible model will predict you are reaching in one case, you are reaching, the rigid body case, you are reaching 50,000 feet, and with the flexible model, you are reaching 80,000 feet. So it's a slight mismatch, smaller and greater. In height, it is height it is, the flexible model is less. In range, horizontal range, the landing distance is greater. So there is a mistake. Yes, smaller in height and lower in landing. Okay. Then the last problem that I considered was, actually I went to Beijing Institute of Technology as a visiting professor, and I taught the students a method which is an extension of Keynes' method called Keynes' method with Lagrange multipliers. Again, this method was not developed by me, but one of Keynes' very old students when Keynes was a young man. It's called Keynes' method with Lagrange multipliers, and I taught them how to use this. And the spacecraft contain like this. There are 4 tanks and there's 2 stubby solar panels, and there were reaction wheels. And on these tanks there were fuels, and as the thing rotates, there will be large fuel slosh. Fuel will be. If you think of one of the petroleum tanks that move about in Calcutta, they have the fuel inside them sloshing back and forth and hitting the wall. So they have to be careful about it. Here, the large fuel slosh puts a side force. That side force is a disturbance to the spacecraft. If it wants to point in that direction, and there comes a side force because the liquid hit the wall, then that disturbance will cause a blurring of an image if the spacecraft is taking images. So I showed them the method of how Keynes' method with Lagrange multipliers. These Lagrange multipliers tell you that it says that I assign some 3 degrees of freedom at that point of the particle. The particles are supposed to be crawling around. This is the model. In the model, the fluid is modeled as a particle with 3 degrees of freedom, with that the particle cannot dig into the surface of the wall. That's the constant. And because of that constant comes one Lagrange multiplier per tank. So the whole physical idea is that I will not let a particle to dig in. It can go up, it can go tangentially, but not normal to the wall. So if you apply that constraint which comes through the use of Lagrange multipliers on a crawling particle, again, this is a particle moving over a moving body. So that's why I said it's a very basic theorem. And so the results were computed by my students and the professor at China. And because I left, so they completed the theory and validated that against a commercially available code called Flow 3D, three-dimensional fluid mechanics code. Look at the beautiful match against the equations of motion model with Lagrange multipliers, and what the computational fluid dynamics model predicted. You see a beautiful match. So that's practically the end, and this is my last slide. Conclusion is, method due to Keynes, who may be thought of as the greatest dynamicist of the 20th century, requires the least labor and produces simplest equations of motion for complex systems. The systems that he considered was, that's a spacecraft with 3 rotors and nutrition damper, etc., plus all the others that I've talked about. And then Keynes' method directly, however, gives a dense mass matrix, computationally more efficient algorithms like order n, which I learned from my colleague Dan Rosenthal, PhD from Stanford, and block diagonal formulation that I developed and are given in the. This is also based on Keynes' method, but it's a refinement. Backward, forward, backward recursion generates this block diagonal mass matrix. They are given in the book, in this book, which was published in 2016, and the second edition is coming out this year. So that's all.
Thank you, Dr. Banerjee. it was a very informative and engrossing talk. Actually, our students and whoever is present here, many alumni of this institute are also present here. Now, I'd like to invite the students and from the audience, if you have any question for Dr. Banerjee, any queries.
Dr. Banerjee,
Yes.
I'm Shantanu Das, a faculty member in the Department of Mechanical Engineering, IIEST Shibpur.
Yes.
Sir, I don't know about this Keynes method. I heard about this, but I don't know this. Thank you for making me learn this thing. And just I want to understand this method. Basically, when you are calculating this active generalized force in Keynes,
Yes.
yes, in that there you don't talk about constant forces. Just like this Lagrange method here, the constant forces are not basically playing any. There it was basically that virtual work was there, so basically that accumulated to zero. But here I don't know what is happening to that constant forces.
Excellent question. The answer is also very crisp. That's why you use Keynes equation with Lagrange multipliers, which I referred to in my slide where there was side forces on the tank. So those are the constraints. So Keynes equations have been modified by this little additional step. You add constant forces and take into account generalized active forces due to these undetermined constant forces, and then you determine them by writing constant equations. So you solved equations of motion involving the constant forces and a second set of constant equations. There are as many constant equations as there are multipliers.
Okay. So is it just like non-holonomic constraint in Lagrange method?
Yeah, right. A transpose lambda.
So
Yeah.
holonomic constant will not affect any anything in the equation of motion. Only the non-holonomic constant will introduce the Lagrange multiplier just like the Lagrange method and do the procedure.
Yes. Yeah, of course, you can convert a holonomic by differentiating it. Yes, right. You can you can convert the holonomic constant into right. You can do that. And now with constants, however, by this Keynes approach with Lagrange multipliers, there is a constraint error in the course of integration. That has been one gentleman from Germany by the name of Baumgarten. So he established a procedure of violation of constraints. He penalized them. So he added a kind of a control term, proportional to the error and another derivative error times another constant, like a proportional derivative control. So that way one can get
Okay.
Is that does that answer your question?
Yes. But I have to study this method in little detail, so then I may able to understand in a more.
Yeah, I think the best way to study is do the problem. Don't read,
Yes.
but do.
That is true for dynamics in general actually.
Anything. By reading one doesn't learn. Yeah.
Dr. Banerjee, Professor
Arindam,
Ashok
can I say
Mollik.
something?
Yes, please.
Arunda, I'm a
Mollik, please.
67 graduate, so I am taking the liberty of calling you Arunda.
Sure, do.
After hearing this expert lecture, I want to share my small experience regarding Keynes method.
Yes.
In 1998, I offered an elective course in IIT Kanpur on Keynes dynamics. This is an elective course. Two graduate students and two undergraduate students took it. Only 4 students in the class. One ordinary teacher and 4 brilliant students tried to follow Keynes and Levinson's book line by line and solve all the problems. So to Shantanu, I want to say the same thing. If you solve those, I think there are 16 set of problems or 12 set of problems, I forget now. We couldn't do the last 2 sets. There are 7 chapters in the book. We could cover only up to chapter 6. There was no flexible body. It was only particles and rigid body.
That's right. Actually, Kane did all his flexible body work with me, you know.
Right. Levinson.
No. Yeah,
Kane.
Levinson. Yeah, Kane and Levinson worked together on rigid bodies.
Right.
By the way, Levinson is.
That is the part we tried to learn in that course. And at the end of the course, 3 of the students have become faculty members, 2 in IIT Kharagpur, 1 in IIT Kanpur, doing research in dynamics. And the other one went to MIT for MS, but got lured by the Wall Street Journal. I don't think Keynes dynamics threatened him. He was lured by the money aspect. He was a very brilliant student, but joined the finance company. So Shantanu, that Kane and Levinson's book is an excellent book. You can read line by line, and you have to solve the problems at the end. If any student thinks that hearing from Arunda will learn the subject in 1 hour, forget it.
No.
It was a 40-lecture course. Still, I couldn't follow, complete all the chapters. And all those 4 are very brilliant students. The teacher was learning only. That I accept. Not that I knew the subject and was teaching. I just wanted to learn it, and they helped me in learning because we solved the problems together.
Right.
So what happened to that elective in IIT Kanpur? It was not offered after that, because when I was a student.
No, it was not offered after that because nobody wanted to learn that method. My objective was to learn it only by offering that course.
Yeah, I think there is a saying that the teacher must teach himself.
Ashokda, was it Anirban? The faculty members now, one is, I guess, Anirban, or?
Oh, sorry. Yes, one is Anirban Dasgupta, one is Gautam Chakraborty, both in IIT Kharagpur, one is Ishan Sharma in IIT Kanpur, and the 4th one is Gaurav Shukla, who, as I said, went to MIT, completed his MS, and now some vice president in some Japanese bank.
Oh, I see. Yeah. So, actually,
just little maybe incongruous. I invited Arunda to IIT Guwahati when I was there.
Oh, I see.
Arunda, we Gautam.
Acha, bolo. You were very kind enough to take me to see the rhinoceros on the Brahmaputra River.
Arunda mesmerized not only mechanical colleagues but entire institute, by solving several problems from Keynes books.
Actually, I did a lot of work with Professor Kane. My involvement was only in flexible body dynamics. The book that I have written is a good source of flexible body dynamics problems. As in my slides, I was showing them. Almost all of them were flexible bodies. And I bought a copy of Professor Kane's book, and Professor Kane wrote that to Arun, with all good wishes, and in the expectation that we'll continue to do more interesting problems together. That was I was overwhelmed. I wrote 7 papers with him, and then I got the confidence. Yeah, I can do it by myself, and then I moved on. All this order and this block diagonal formulation, I actually were developed by me. Particularly the block diagonal with geometric stiffness. It was much appreciated. That's why European Space Agency called me to give the talk. And I have gone to Warsaw and Adelaide, Tokyo, speaking about these things. So it has been an enchanted life because of these things.
I think Professor Amitava Ghosh wants to say something. Professor Ghosh.
Bolo Amitava.
Arun is the only one amongst my known
personality who has 2 PhDs from 2 reputed world-class universities. So it is, I think, what you have heard today is the tip of the iceberg of Arun's work. And we reconnected with Arun because he was our roll number 1, most probably. And we used to call him all the class. Actually, you know, amongst friends, there is not much of respect. You know it very well in classmates. But Arun used to be held in high esteem, and we used to maintain a respectful distance because
Hey, I didn't know that.
strong in English. And we used to call him as Shikumar Banerjee of our class, you know. So, and one thing I would like to mention, it is, of course, in a very personal note, Arun was very dear to my parents, though Arun never had the reason behind it. He never knew about it. The reason is very simple. After giving the BTech examination or bachelor's examination, I went home, which is a remote village in Bengal, in the border of Bihar and Bengal. And then I think I was away, I went to some place, and our result was out in the meantime. And Arun wrote a postcard to me, to my village address, giving my result that I did well. And that, of course, though I was not home being a postcard, my father read it and they got the news. And from that day, Arun was in their, Arun was one of the, what I'll say, they are most dear to my parents because they got the news about my graduation from Arun. Arun never knew that, and I have never told this to Arun.
ওনারা কি আছেন?
হ্যাঁ,
ওনারা কি আছেন এখন? বেঁচে আছেন?
না, তা থাকে না। আমার নিজেরই 81 বছর বয়সে ওনারা কি করে থাকবে?
I send my pranam to them in heaven.
But I think all along, I remember my father used to talk about you, though you never met him and he never met you because of your postcard.
Although I will add, you know, something to this anecdote. Incidentally, I was very close to Professor G.L. Sinha.
Hey!
And Professor G.L. Sinha always used to say that the best learner and best student he has seen in his entire life is Arun.
ও ভাই, তুমি আমাকে একটু একটা খবর দিলে, এটা আমার digest করতে অনেক টাইম লাগে, তো I am very grateful that you...
I think I must tell you, Arun had extremely bitter experience at IIT Kharagpur because of one person. I will not name him, but I think, and he had more or less, that was one of the reasons he left India.
You don't need to mention, everybody knows.
Yeah, but Professor G.L. Sinha used to, you know, always admire him. Always admire.
I'm
a very serious person. I think the kind of discussion, very light, sometimes not speakable words are exchanged among students. I think Arun was not at all like that. He used to be quite different in our class, and we always used to love him and also respect him.
এই ভাই, তুমি আমাকে লজ্জায় মাটিতে নামিয়ে দিচ্ছ।
না, অনেক দূরে আছো তুমি অরুণ, তোমাকে পালো আল্টো থেকে আমি কি করে নিয়ে আসবো?
We are also getting to know a lot of things about you.
Any more question?
Yes, any more students?
তোমার ইংরেজিটার অনেক জ্ঞান আছে, সেই জন্য আমি তোমার কাছে একটা অ্যাডভাইস চাইছি। IIEST Shibpur honored me by offering, Dr. Arun Banerjee actually, offering a position of honorary distinguished professor. Now, can I also slightly change it to honorary extinguished professor now?
Yeah, surely.
Okay, I will now onwards write that then.
Yeah. I'm actually extinguished professor.
Yeah.
Also, because all the crimes that I follow.
আমার একটা প্রশ্ন ছিল, although I am not expert in this area. I have a degree in mechanical engineering from Jadavpur University, but after that I moved on to a different area. As you have been talking about,
okay.
As you have been talking about the computational burden of the Lagrange's method, relaxes it. So is there any trade-off with respect to accuracy and efficiency of the method that we are going to, that is being done by Keynes method?
Well, there are tests that you can set up whether your equations are correct or not. For example, do the angular momentum check. Angular momentum about the system mass center should be constant in the absence of external forces. You can do some, and it has never been found that there is a, if the equations are correct, then there is no problem with accuracy. Accuracy is related to the integrator that you are using. If you are using a Rangekata RK4 or RK45 in MATLAB, then first of all, you have to form the equation. That's where I'm telling that you can even form the equation using Lagrange, Hamilton, and Boltzmann-Hamel methods or Gibbs methods. Whereas you can form the equation. You first have to have the equations. Then you can talk about.
I think, Arun, I would like to interject here. You are very correct. I remember that in 1974-75, one of my postgraduate student at IIT Kanpur, he used Keynes method. And I used to also consult his book, Dynamics, that green cover book, if you remember.
Right.
So I think even handling non-holonomic systems, he developed or he solved his problem of a specialized cycle rickshaw using Keynes method. And that was in 1974-75.
Oh.
And I think handling even non-holonomic systems also is much easier, or at least sometimes convenient if you use Keynes approach.
Yeah, right.
Okay,
And,
sir, I had another question. Yes, please. Arunda, please continue. You wanted to say something.
আমি typically আমার industrial problems গুলো আমি করি কি directly Keynes method use করি না on to treat non-holonomic constant. What Keynes does is you have to eliminate some of the generalized speeds that are involved in the constraint equations and work with a reduced number of generalized speeds, n minus m. If there are m constraints and n degrees of freedom, so you will have n minus n and add m Lagrange multipliers. And so with the n plus m, basically it is the same thing. What Keynes method with Lagrange multipliers does is basically
non-holonomic constraints you cannot eliminate, and it's exactly Lagrange multiplier technique is used in such cases.
Yeah, right.
And another thing which comes to my mind, it might not be a great question or might not be related at all. I was just thinking that this dynamics of elastic multibody spacecraft, do you take into account somehow the general relativity? Does it come into play?
No. Because I don't know anything about theory of relativity. Actually, most of the things are of a slow speed, compared to the velocity of light. So I think relativity terms are not considered, right. So.
And how are these simulations done?
Simulations are done. First simulations are done this way. First you write the equations of motion. And because I'm an old man, I know only Fortran. I don't know any other language, So I used to write it in Fortran, the Fortran code, where in the main driver routine, there was the Rangekata code, and the code would call the function to be integrated. There are n degree of freedom dynamical equations and n degree of freedom kinematical equations. So they were spelled out in the body of the code, and then so those differential equations are coded, nonlinear differential equations, sent to the integrator, and the integrator would give you the output and plot it. Later, people used it in MATLAB. I have forgotten, about. I have not been using MATLAB for 12 years.
So in MATLAB OD45, that is Rangekutta fourth order solver is there. But for the that stiffening, if the derivative is stiff, there are other
yeah.
OD113 or something else.
Yeah.
There different codes are there. So you have to
differential algebra.
write it in a state space form, and then you can integrate it. Nothing.
Yeah, right. Yeah, those are called the differential algebraic solver, DAE.
Yes.
Yeah. Linda Petzold at University of Minnesota developed that. And Charlie Gear. So,
Okay.
yeah.
Okay, Arun, I think all the very best. We had a very wonderful time. And I'm sure that in subsequent lectures, we will also find you joining, at least not all, but in some lectures.
Thank you. তুমি আমার নামটা নিশ্চয়ই দিয়েছিলে বলে আমি বলার সুযোগটা পেলাম। I'm grateful to you for that. ভাই।
তুমি আমাকে ঝামেলায় ফেলছো। I think it was wonderful. I think তুমি এখানে খুব অত্যন্ত পরিচিত, তার কারণ অধিকাংশই হয়তো অত খেয়াল থাকে না যে you have donated a huge amount of your personal money to your alma mater.
Yes, that I wanted to mention here. There are many students here. Dr. Arun Kanti Banerjee has donated ₹1 crore for Alpana Banerjee Memorial Endowment Fund, which is for the innovative projects. And due to COVID, we have not been able to implement some of them. But I'll request all the students, mainly it will be used for the students' projects. All the students may come up with innovative projects. From there, a lot of money is there which can be spent for the innovative projects. So that is, and for that we are really grateful to Dr. Banerjee that he has contributed his personal money for the betterment of the institute in a big way. Thank you so much, Dr. Banerjee.
Big hand.
You're very kind, but আমি ভাবি যে পড়াশোনা তো যা নিয়োজন, কিন্তু পরে কিছু করতে পারলে আমাদের দেশে, আমি সেদিনকে সত্যনারায়ণ পুজোর পাঁচালির কথা শুনছিলাম, আমার মেয়েটা পুজো করে, তাতে বলছে যে পরহিতের অত যেই ধার্মিকের শ্রেষ্ঠ সেই। হ্যাঁ, তো ওখানে আমি দেশে 5টা জায়গায় পয়সা পাঠাই, দুর্গাপুরে, মিজোরামে, অরুণাচলে, আর তোমার বোলপুরে সাঁওতালদের কাছে, আরেকটি জায়গায় কিছু মুসলমান সম্প্রদায় আছে, কেন্দুলি, জয়দেব কেন্দুলি গ্রাম। তো এইটা দিয়ে নিজেকে সার্থক মনে হয়। আমার তো এবার তো চলে যাওয়ার সময় হলো, হরিদিন তো গেল, বলে গাইতে হবে এখন, পার করো আমারে।
Wish you long life.
Wish you long life. Arunda খুব ভালো থাকবেন, Yes, over to Professor Sudeep Ghosh.
Yes, and on behalf of the department and also on behalf of the Centenary Celebration Committee, I must thank our today's speaker, Dr. Arun Kanti Banerjee, for giving this enchanting lecture. So nice lecture. It might be a little longer. And I hope we will be able to arrange some short courses together with the Applied Mechanics Department. I have already forwarded your proposal to the Dr. Banerjee's proposal to Applied Mechanics Department. If they come up with some proposal, we might look into that. Probably sooner we will get a short course for the students, and we'll get him once again here in this platform, maybe online or if possible in offline mode also. So thank you, Dr. Banerjee. I must also take this opportunity to thank our today's chair, Professor Anindam Vishwas, for giving us time and hosting this event, leading the event so nicely towards its completion. So I should also thank our senior members of alumni, Professor Ghosh, Professor Mollik. I have also seen Kamulda coming here. I don't know whether he's still there or not. I didn't hear anything from Kamulda today. Palit is also there. A lot of senior members of alumni have joined today. Professor Gautam Vishwas is still there. Thank you, sir, for joining. So with that, we would, and one last responsibility I have, I would request our session chair to virtually hand over certificate of appreciation to Dr. Banerjee. Do you have a copy, soft copy here to show here? We also have a memento. Yes, and the hard copy of this certificate we should be sending along with the memento. Till that time, we'll be keeping it in our department. And if we happen to get you sometime here within India, then we might find it easier to hand it over, the memento as well as the hard copy of the certificate. And the soft copy of the certificate we'll be sending through mail. So thank you very much, sir, once again.
Thank you. Thank you.
So,
God bless you.
Thank you.
thank you, sir. So we can stop the recording, Shantanu, and volunteers, we might close it here.